Thank you for coming back again. So how does Daisy score? So how do we eliminate underperforming ads? So let's get rid of ads that aren't performing well and replace them with ads that perform well. And as I said, this is not just about promotions. We're getting at the total store, promotion plus non-promotion, but through the lens of promotion by choosing what to promote and what not to promote. So it's that full merchandise mix you're looking at. So there's two things we can do. We can measure historical performance. So all of the things I've shown, we can do that to measure historically what happens, and that's what we've talked about so far. And you can glean insights from that. We can do backward kind of scoring and show you what works well, what doesn't work well. And you can also predict ad performance. If we can simulate the future, we can predict what the ad performance is using all of the same metrics that I described so far. And so this is what Daisy's AI does. We simulate the future using reinforcement learning or optimal control. And because Daisy ranks every decision, we try to create a simulation that contains the best aggregate ranking promotions on every channel. So the combinations that have the best rank will drive the best outcome. So Daisy provides the rank, which is based on the relative index, and I'll describe how we calculate that. And we provide some simple green, yellow, red indicators that are related to the rank to make it easy to choose the best decisions. So green decisions are better than yellow decisions, are better than red decisions. The number 1 rank is better than the number 100 rank, and the relative index is related to the actual incremental sales or incremental margin or incremental traffic that we simulate. And so the Daisy rank is strongly correlated to total store impact. So looking at the average Daisy rank of a promotion, it's a negative line because number 1 is the best, and obviously a high TSI is good. So the lower the average rank, the higher the total store impact. So each dot here is a weekly aggregate promotion, and we can see this is about a negative 0.5 correlation for this example from a real customer. So choosing better average ranked products creates a higher total store impact, this strong correlation. And the higher the total store impact, the higher the same store or like for like store sales. In this example here is about 0.6. We typically see this is unadjusted ranks, a complex discussion there, but typically if we have an adjusted rank, we get correlations that are on the order of 0.7 to 0.9 related to total store impact, and we get like for like impact 0.8 to 0.95 TSI related to year-over-year comp store sales. So the path is and it's highly nonlinear. So the Daisy rank is very nonlinear. So the best items, if we're looking at the Daisy rank, here we've inverted it. So the lowest rank have the highest sales and associated sales. You can see these dots way out here. So it's highly nonlinear. And a lot of items with a very high rank, so these are your poorer items, have a very low sales and associated sales, but the rank is nonlinear. So your best items are much better than your worst items. So you can't just do simple averaging. In those previous 2 graphs, we just showed simple averaging. So if you do complicated nonlinear averaging, that's how you get very strong correlations. So we have this causality. And here we've plotted green items versus yellow and red together. We combine the yellow and red. Typically, green items are the top 15% of items based on the Daisy rank. And here we can see in 100% of weeks, the green items outperform yellow and red. So this is almost a perfect leading indicator at this level here. And Daisy can create these stoplight indicators months in advance of your promotion. So because of this fact, you can use this to make optimal decisions. You don't have to choose all green items. Typically, you start with a new customer, about 30% of items are green versus 70% being yellow and red. So we can do more green items. Getting it up to 70% plus green versus yellow and red will drive total store impact 3 to 5% total company sales. So that's that promoted sales plus non-promoted sales, summing that total weekly sales result. So very strong correlations I've shown between the Daisy rank. Again, a very granular leading indicator right at the item level, the item price level, at that most micro level that you can make a decision at. Aggregating that metric shows a perfect leading indicator here with 100% of the time green being better than yellow and red. So this is telling you the AI is great. You can take advantage of it to do better, because when you have a better rank, you have a better total store impact, and you have a better year-over-year comp store sales that I showed through those correlation effects. So the average rank of a green items are about 191. The average rank of the yellow and red is about 700. So there's a big causal difference between these items. So the general approach, as I said, high performing ranks, products and price points of better rank. Items with a better rank generate higher total store impact. Higher total store impact generate higher comp store sales. So that's the game that our AI system plays. So how do we simulate? Already talked about this halo, which occurs in all your high frequency items. Now there's multiple effects going on. We're not building a predictive model. I get asked a lot of time, what's your model? How do you fit the model? We're using a different approach, the approach of science. So not really a different approach. This is what scientists have done. We've created a theory of retail, like there's a theory of the laws of physics. And so there's multiple effects going on in retail. So in bricks and mortar retail and e-commerce, there's analogy e-commerce. You have a market out there here. If we show kind of the curvy line as the retail market, all the green stars are store locations, and these little circles are households. So households will go to stores and buy stuff. This is analogous to gravitation or potential flow scenario, which is, Laplace's equation, del squared phi equals 0. If we treat the stores as sinks, that they suck in flow, and the households are sources of people and money. So the people go from a source, people take their money and go to the sink and spend their money in stores. So we can model this geographically in macro to say we can estimate what the effect of the store location and people locations, and there's a dynamic effect of promotion, because promotion affects the strength of the store sinks. So we can affect the attractiveness of the store by using promotion. So we can think of this gravitationally. If you look at the gravitational wells of our solar system, we can see Jupiter and Saturn, large planets, have large gravitational attractiveness. So similarly, the analogy is very attractive stores and large stores have more attractiveness. Consumers are willing to go farther. Jupiter has a longer distance gravitational impact that's significant than Mercury does, right? It has a smaller well. So in the same way, a large attractive store has more of an impact on people that live farther away. You are willing to drive farther to go to an attractive store, and a store that furthermore has attractive promotions, has a good daisy rank, that will dynamically impact this promotion. There's a baseline effect of store size and brand attractiveness. We know the brands from all the advertising and our past experience, but also having good promotions will dynamically increase this gravitational attractiveness. Similarly, in e-commerce, there's a similar concept. The attractiveness of great websites, great e-commerce sites will drag more traffic, and you can dynamically impact that by the promotions that you do. The difficulty in finding those websites and navigating those websites is analogous to how much advertising you do. So it's not a drive distance to the store, it's how easy it is to find the link to that e-commerce site. And typically that's based on how much advertising, how much social media is available. So there's an analogy in e-commerce. We can model this like a gravitational potential. There's also traffic flow. So in a bricks and mortar case, if you locate a store in a plaza, a lot of grocery stores are located in outdoor plazas. So that outdoor plaza attracts a lot of gravitational traffic. And so the higher the traffic driving by a store, the more likely you'll capture some of that. So there's this gravitational effect. There's also the effect of traffic. And that's why grocery stores are usually also near large population centers, and traffic coming into and out of large population centers is part of the effect as well. So stores drag some percentage of the traffic flow. So that's the macro level effect that's going on. Traffic based on population density and road configuration, as well as store attractiveness, store size, and promotional attractiveness. These affect the traffic flow, the likelihood that a person living at point I goes to a store at location J. And there's a probability that that happens based on this Laplace's equation. Similarly, once that traffic comes in the store, we can model the traffic walking in the store layout. That also drives traffic. So where the products are in the store, how difficult the products are to find, we can calculate the traffic to the store. You can observe this with cameras and Wi-Fi tracking, which is very costly and expensive. We can also calculate it by knowing the store store layout, knowing where every product is on every shelf in the store, knowing the transactions, the items that were bought. We can assume the customer took an optimal path through the store, add some randomness to that, and we can actually calculate the traffic through the store. And we know that aisles with higher traffic have a higher conversion to transactions. So traffic is people coming in the store, and then a conversion factor applied to traffic that determines the number of transactions. And location in the store, where you put the products, where on the shelf, eye level or floor level or above eye level, that impacts conversion rate. So the XYZ location of products can be used to impact conversion. And so we can use this to drive space planning. The macro level determines where you should put your stores, how big you should make them, or how much advertising you should do on the internet to drive traffic. This here now looks at the micro level of the store. What product should we have in store? How should we lay out your stores to maximize the traffic through the store and maximize the conversion rate? So that's a micro level traffic problem. And then finally, if we plot year over year sales, so this is a retailer, this is 2 years of sales laid on top of each other, where we've holiday adjusted the holiday events. So Easter typically moves by a month, Christmas moves by a few days, Thanksgiving typically is the first Monday of October in Canada. So if we align all the holidays, we can see the difference between the year to 2 years is very little. You know, this is a well-established retailer, not in high growth mode, so they're, you know, growing slowly. But those little green areas are the difference in year over year sales. And those are typically 5 to 10% are the year over year differences. And by optimizing the mix of items, the mix of prices, the placement in stores, we can drive more or less consumer traffic based on that macro view. We can drive more or less halo based on doing the right combinations of items. We can drive more or less stockouts by doing the better forecasting and ordering. And we can take advantage of all these cyclic trends that occur seasonally, like the Christmas, the events, the holidays, weather, all of these things. So optimizing this kind of halo impact, we can optimize the year over year difference. So macro geography, micro geography, halo patterns, and year over year comp store sales. That's what I've laid out so far. We can collect data for the market level view, spatial allocation data, looking at things like street network data, the street network files publicly available, all the residential addresses, where do all the people live, what are all the addresses, that's publicly available data. Geodemographic potential, we know the approximate household income and household sizes of those that can be purchased in Canada. Census data, US, that's generally free. We can calculate the known customer potential. We know what consumers spend typically on food purchases based on their income and geodemographics. We can calculate what your site attractiveness is relative to the competitors. We can calculate the dynamic impact of your promotions on that. We can calibrate this macro Laplace's model to your historical sales. In store, we can look at your store layouts and fixturings. We can look at your planograms and where your products are, your XYZ locations, products in your store. We can calculate from the T-log, we can calculate the optimal path that the consumer must have walked to buy the items that they had in their transaction, add a bit of randomness to that. And if you've got measurements in a small number of stores, we can calibrate this randomness to be able to accurately calculate the paths that consumers take through your stores, calculate the product affinities to see how we can optimally lay out your store to maximize this halo effect that we've talked about. You can use this for labor scheduling, and we can fit this to all of your history as well. And then looking at that store halo optimization, this is using your T-log data to calculate the product affinities. As we said, it's a calculation. We can calculate those associated sales, cannibalization, cadence, all of those that we talked about earlier on. You could use some social media data, seasonality, competitive price data, competitor promotions. We know weather has a backwards looking impact, harder to predict weather. We can calculate elasticity and cross price elasticity of your items. We can calculate the location of items in the store over all of history. So these are the 3 different kind of equations. These are now partial differential equations like the laws of physics. The general theory of relativity is a set of 10 coupled partial differential equations, elliptic and hyperbolic equations. And here we've created a similar set of differential equations. We can solve all three of these in a coupled equation set, or we have boundary conditions and initial value problems. We can apply a boundary condition between the micro optimization and the halo effect, which is the transaction count. There's a boundary conditions between the market level and the micro level, which is the store traffic. So we can assume boundary conditions and initial values to solve the PDEs, or we can solve them as a full coupled set. And you can read Daisy's patents online to see some of these patents. So here we have Laplace's equation or Poisson's equation. We can add a potential function to the macro market or the e-commerce market, and we can define potential function, which is a function of store attractiveness, how difficult it is for the consumer to get to the store, how attractive your promotions are, your historical retail performance, where the consumers live. So we can drive a potential function using some spatial allocation model like the Wilson model or the Huff model or something more complicated. We can define a path integral through your stores that depends on the gradient in traffic through your store, the store location, where the items are in the store, what the planogram is, where the XYZ location of items is. So calculating that path integral, converting traffic into transactions. And then we can look at what the incremental year-over-year difference in sales, what's that D sales over D time or any sales metric, sales, gross margin, incremental traffic, which is a function of your items that you promote, the halo items, what are the product affinities, what are your combinations of items, what are the combinations of prices, what's the inventory availability of the products, what's the promotional channel mix, how much do you promote on each of your channels, seasonality, what's the transaction forecast based on the overall promotional attractiveness. And we can say the incremental sales is proportional to the incremental quality of your promotion. That's generally what this differential equation says. So here's a set of coupled differential equations that we can solve. You can read the Daisy patents if you're interested to get some algebraic forms of these equations that we can simulate. And we can simulate the future. We can say, what is the optimal set of items? So imagine feeding into those differential equations a vector, a binary vector. If you have 50,000 items that says promote, not promote, 1, 0, 1, 0, 0, 0, 1, 50,000 long, which says promote or not promote each of those items. We can feed in a vector of 50,000 prices. What are the prices of each of those items for each price zone? So if you have 10 price zones, there's 500,000 long vector, which each of the unique prices. We can feed in an order for each of the items at each store. So we can do, if you have 100 stores, we have 100 times 50,000 allocations of items to each of the stores. We can feed that vector in to the differential equations, and we can say, what is the optimal outcome? So if you imagine an n-dimensional surface now, we find an optimum. We won't find a global optimum, as I said earlier, because the search space is much too large. 10 to the 3600 is impossible to search, but we can find local optima that are better than what human beings can come up with this because of this very computational nature of this. And we can then calculate what is the individual decision's contribution to the optimum solution. What is the individual item's contribution? What is the individual price point's contribution? So you think now we have an n-dimensional space of 50,000 items, and we can now we can calculate the partial derivative to say if you're doing 2 items in this category, take away 1 item, that's an increment from the optimum, or adding 1 more item, that's an increment to the optimum. It should be an increment away from the optimum. If you found an optimum moving in any direction, in any item direction would be going away from the optimum. So we can calculate the value of that last step into or out of the optimum. We can calculate that one at a time for each item, each of the 50,000 items, calculate its contribution to the optimum solution. So we can calculate its incremental sales, margin, or transaction contribution, that last item that you add to the promotion. What did it impact to the promotion based on our differential equation simulation? Similarly, we can say what's the impact of the last price point change that we evaluated into or out of the optimum, and we can provide a relative metric of the price impact. So we can calculate a price rank and an item rank, and that's how Daisy creates this rank. We rank every item in a particular week and its ability to drive incremental impact to that total store waterfall. We calculate an incremental price point to show the incremental impact of every price to that total store impact waterfall by using this analogy of partial differential equations in an n-dimensional surface, which is your optimal solution. And as I said, DAISY then translates that relative index, which is this incremental impact of every item and every price. We turn that into a rank. We rank the relative index to turn that into the best item to the 50,000th item, and the best price point to the 500,000th price, because we might be evaluating 10 prices per item. And then we color code that, the top 10% being green, the next 15% being yellow, and the bottom 75% being red. So we provide this guidance to help our clients make the best possible choices. And I said earlier, the DAISY ranks at the stoplight indicator level, it's 100% correlated to outcomes. At the DAISY rank level, it's roughly 0.7 to 0.9 correlated to financial outcomes. So very strong leading indicators that can be used to make the best future decision. And then measuring backwards, you can validate that, in fact, the good outcome that I wanted happened. Remember, the DAISY rank negatively correlated to store impact, the total store impact positively correlated to year-over-year same-store sales. Again, this rank is highly nonlinear. Your best items are orders of magnitude better than your worst items. The stoplight indicators are 100% correlated to outcomes. This is a forward-looking indicator showing that 100% of the time green does better than yellow and red, and the same will hold for backward-looking when you measure it on a backward-looking basis. In most cases, it'll be 100% correlated. So the game is simple. Choose better performing items and the best performing price points using the DAISY relative index and the DAISY rank. If you do that, you'll get a higher total store impact, both, which is a promotional and non-promotional impact. It's getting at your whole merchandise plan through your promotion decisions, and that higher total store impact on a weekly basis results in higher comp store sales year over year. So if you want to improve your sales, improve your weekly total store impact, improve your promotions, which improve your overall regular performance as well. And that's what I had to say today. So a lot of content. There's some patents on the uspto.gov that are published, that are some granted patents and some are applications that are public domain. You can look at some more technical detail. But what I've described here is simulating using a set of differential equations like the laws of physics. And we use machine learning and other machine learning techniques to calculate sophisticated features like affinities, like the halo, like elasticity. We do machine learning forecasting that needs to preserve the halo. Your forecast needs to preserve that halo ratio. So using sophisticated machine learning techniques to calculate very intelligent features that we then put into our differential equations, and then we simulate to say, what is the optimal decision? What's the optimal combination of products, the optimal combination of prices, the optimal ordering, the optimal assortment, the optimal placement of items in store, and we can assess and simulate the future to make the best decision today and the best sequence of decisions, because it's the sequence of decisions over a 52-week period that will result in maximum sales, maximum profit, maximum traffic, maximum customer sat, maximum market share. So this is the DAISY brand of reinforcement learning or optimal control, a brand of generative AI that's different than large language models, based on the scientific method of create a mathematical theory, because it's beyond computational ability to learn Einstein's equations from the data. It's impossible to learn the theory and dynamics of retail from the data. Thank you for joining. You can subscribe on Spotify and YouTube to this channel. I welcome conversations, guests. If you want to debate and you violently disagree, or you agree, or you want to find out more, don't hesitate to reach out. Thanks so much.